Today, we're going to dive into a statistical puzzle that's kind of hiding in plain sight. It's a concept that sounds super simple, perfect consistency, but trust me, it has the power to either validate a huge scientific discovery or crash the very algorithms that run our world. We are talking about what happens when you get a standard deviation of 0. At its heart, this is really a story about change. I mean, we understand the world through variation, right? The ups and the downs, the ebbs and the flows. But what happens when everything just stops changing? And that's the real question, isn't it? What happens when something we expect to change, like stock prices or daily temperatures, suddenly becomes a constant? It's called a variable for a reason. When it stops varying, you get this weird paradox that really challenges what that word even means. Okay, so this image here shows the idea perfectly. On the right, you've got a typical data set. See how the points are scattered all over? That's variation. But now look at the left. Every single data point has collapsed onto one single perfect line. There's no spread. There's no difference at all. That is what a zero standard deviation looks like. So, just to make sure we're on the same page, standard deviation is our main tool for measuring this spread. It basically tells us, on average, how far each data point is from the middle, or the mean, of the whole set. So a big standard deviation means your data is all over the place. A small one means it's all bunched up tight. So how exactly does this perfect consistency give you a standard deviation of exactly 0? Well, the answer is locked right inside the math. And honestly, it's surprisingly simple. Calculating it is really just a few steps. First, you find the average of all your numbers. Then, you see how far each number is from that average. You square those distances to get rid of any negative signs, find the average of those squared numbers, that's called the variance, and finally, you just take the square root. Boom, that's your standard deviation. And here's where it all clicks. Look at this side by side. Dataset B on the right has numbers all over the place, and it ends up with a standard deviation of about 1.64. But now look at dataset A. The average is 5, and every single data point is also 5. So the distance from the average for each point? It's 0 every single time, which means the sum of the squares is 0, the variance is 0, the final standard deviation has to be 0. So here's the crucial takeaway. Perfect consistency isn't just an idea, it's a mathematical guarantee. If all your data is exactly the same, the standard deviation will be 0. It's the only possible outcome. The math says so. But here's where it gets really interesting. A 0 standard deviation isn't just a number, it tells a story. And depending on the context, that story can either be a massive success or a huge red flag. The easiest way to think about it is this. There's a good 0 and a bad 0. A good 0 is something you get on purpose. It's a sign of control. A bad 0, well, that happens by accident, and it's a warning that something's really wrong with your data. For instance, a good 0. Imagine you're a scientist running a chemistry experiment. You need to hold the temperature perfectly constant to see what happens. If you measure the temperature throughout the experiment and its standard deviation is 0, that's awesome. It means your control was perfect. That's a win. But now let's flip that coin, the bad 0. Imagine you're studying traffic accidents in a huge city. You only collect data for Tuesday and Wednesday, and by sheer luck, there are no accidents. Your sample's standard deviation is 0. But does that mean the city is perfectly safe? No way. That 0 is a bad thing. It's totally misleading, and it's a giant sign that your sample is way too small and doesn't represent reality at all. And this whole good 0, bad 0 thing, it's not just some nerdy thought experiment. It has massive, real-world consequences, especially in the world of data science and machine learning. In that world, a lack of variation isn't just misleading, it can be catastrophic. So here's the root of the problem. A variable that doesn't vary gives you 0 useful information. Think about it. If a piece of data is the same for every single person in your dataset, how can it possibly help you tell them apart or predict what they'll do? It has no power to explain anything. It's useless. To see how this literally breaks things, let's look at a super common formula in statistics for something called a z-score. You see this everywhere. But the most important part for us is that letter S on the bottom. Remember what that stands for? Standard deviation. So what happens if that S is 0? Well, what did we all learn in grade school math? You cannot divide by 0. It's like the one unbreakable rule. For a computer program, trying to do this often means one thing. It crashes. The whole process just grinds to a halt. And that computer crash is just the start of a domino effect. First, the variable has no predictive power. It's totally useless in any kind of model. Second, it can't tell you the difference between any of your data points. And finally, a lot of really advanced and powerful machine learning models will just completely fail. They'll throw up an error and refuse to run because the math just doesn't work without variation.
So, after all that, what's the big takeaway here? Why should we care about this seemingly tiny statistical detail?
Well, it all really boils down to this one powerful idea. To understand a world that's constantly changing, you need data that actually changes too. Information, prediction, understanding, it's all rooted in difference. If your data doesn't vary, it can't explain why anything else varies.
And so I'll leave you with this to think about. In our world, which is so obsessed with data and finding patterns, are we paying enough attention to the nature of that data? What important stories, what crucial warnings are hiding not in the averages we calculate, but in the variations we might be tempted to ignore?